Okay. So some of you let me know whether you refer to the oral final or homework free on multigrid. Now, this might sway your choice a bit. I thought, well, okay, I want to be able to talk about homework free soon. I'll be back to start on it, so I'll just code it up myself. I can't get the dang thing to work.
What did you say?
I can't get the dang thing to work. This is like the first of the homework multigrid problems. This is problem 6, and I have a working, Gauss-Seidel or SOR procedure. I've done both, no problem. I'm not happy with how slowly they converge, but they do converge. And I didn't want to make it converge all the way, so why do multigrid? Okay, well, this is converged to a tolerance of 10 to the minus 5, something like that, and multigrid can finish off the rest. Besides, it converges slowly. And I have working procedures to transfer vectors between a coarse grid and a fine grid. Like if I plot them both, they look the same. So all of that's perfectly fine too, and that's something I could talk about. But for some reason, putting all these working pieces together produces something that doesn't really work all that well. In other words, you get a solution that's only as accurate as what the smoother gives you. The actual correction doesn't really seem to contribute anything extra. And I've been playing around with it, and it's just driving me nuts. And one thing I found was that if I solve a problem AX equals B, or I'll just go AU equals B because X is X values. AU equals B on a fine grid, and then I have it fairly accurate, like 10 to the minus 5, like what my smoother gives me. If I take all three of these things, my solution, my right-hand side, my matrix, and transfer them all three to a coarse grid, it's totally inaccurate. So I'm not sure what I'm going to do about that. So my plan for today is I will take any current questions on homework. We'll handle that, and then I will just continue covering what I have left to cover, and I will later today try to solve that mystery, and then whatever happens, I'll talk to you about that tomorrow. So I'm hoping that the fact that I wrote this when I was not feeling well last night is a significant factor, and that it did something insanely stupid, but it's just driving me nuts. Like, okay, so, and I confess to being a little embarrassed by this, but let's see what happens. Okay, so as far as oral is concerned, so we can use the class time on Friday for those of you who want to do it then, or it can be done at a different time, like on that day, like later in the afternoon. But so I haven't firmly scheduled anybody yet. Okay, 2 of you are not here, but so who? I'm guessing Haley will do a multigrid no matter what. But
Yesterday she said that she wanted to try first problem. Yeah. And if it took her longer than 45 minutes to get somewhere, she was going to.
Oh, okay.
I don't know.
Well, based on my experience, then. Yeah. So, all right, we'll see about that then. We'll see. Well, I'll see her tomorrow anyway. So, okay. Who is interested in taking the oral on Friday? Okay. Well, and that would be enough of you to fill the class period. You're leaning towards homework free. Also homework free? Okay. All right. So we'll make it a viable assignment somehow. Okay. Anyway, whatever's going wrong, I want to resolve it today. Okay. And then, Tavish is remote, so we'll see how that can be worked out. And then whatever Haley wants to do. Okay, so, but we're looking at, well, I guess we could handle all 4 of you during the class time, roughly. So, yeah. Or like basically between 10 and noon. And what I can do is I could just be there in my office, and whoever comes in, comes in. But it doesn't matter who. It's like, oh, it's you first. Okay, whatever. Because, obviously.
Just suppose everybody come the last session, which is the last 30 minutes.
I'll
Okay.
show up around 10.
Okay, yeah. So, in other words, you guys sort out among yourselves, but I want a steady stream of people.
Okay.
Okay. All right. So that'll settle that pretty easily. Okay. All right. Well, are there any homework questions? Like I'm assuming homework 2.
Yeah.
Okay.
So, part A and part B, does this look?
How many points?
400, I think.
Okay, and are you?
As I increased epsilon, I saw that Gibbs phenomenon happening.
Yeah. Now, one thing is, if anyone shows me any graphs, I need you to make dang sure what value of epsilon you're using,
Okay.
because that totally affects the behavior.
Okay.
So.
Now this is epsilon 10 to the minus 4.
Okay, yeah, that's what I would expect.
Okay. Now I do have a question about part B. When we made the matrix, D, the n entry was n. So when we squared it and did all of that, then it blew up.
But okay.
Yeah, when we solved, we got NaN for all.
Sounds like an indexing problem with your points.
Okay, I was wondering because what I did to make it work was remove it.
Well, okay. One thing I want to be clear about is, since D as a whole is n plus 1 by n plus 1,
Okay.
once you include the boundary points. So you're talking about, so you mean the n or n plus 1 plus 1?
Okay.
N minus 1.
Yeah, that was the size that we got. Now, that may have come from. What was the.
Then we took off the last one.
But before that, we couldn't. When we were making.
I think it was our X. So we made our X
From 0 to n.
Yeah, that's your x values.
It said that you can't assign logicals something. So we started from 1. So do we need to tack on that?
Oh, okay. So, thing is, sometimes you need to shift your indices, because since the championship points are numbered in formula from 0 to n, but if you're like assigning them to a vector, then your vector will be indexed from 1 to n plus 1.
Okay. Okay.
So yeah, but there's one thing, that's one of the tedious things about translating mathematical formulas into code, is that we like to number from 0, but MATLAB numbers from 1. And I just want to make sure that you have a right overall process, that you are making the entire D, including boundary entries, squaring that, and then trimming the first and last rows and columns.
Okay. Well, we did make D, and then squared it.
Yeah.
But when we made D, it was 399 by 399. When I'm using n equals 400.
Okay, yeah, definitely something's wrong there, because I would expect that if you're leaving out the boundary rows and columns, because it should be 401 by 401.
Okay.
So, can you show me this is where you're making the matrix?
Okay. So that's where we made X from 1 to n, and then D here.
Okay.
1 to n minus 1. Maybe. Oh, that's why 1 to n minus 1. But I thought it was just for the interior point.
Yeah. Well, but you're leaving out the outer part of the matrix.
Okay.
If you look at page 25 of the notes, where. Yeah, because what happens is the matrix has this freaky block structure Okay, so all right, so make sure. So first, your Chebyshev vector has to have all n plus 1 points in it.
Okay.
Number from 0 to n, formula with index from 1 to n plus 1.
Okay.
Then that'll be enough to make all of this. Then square, then trim.
Okay. So then square, and then you cut off the
First and last rows and columns.
rows and columns of the whole.
To end up with an n minus 1 by n minus 1 matrix in the end.
Okay.
Yeah.
So it'll be enough to, when we're making x, to say j goes from 1 to n plus.
Okay, all right, sorry.
Okay. So it'll be enough to, for our vector x, when we're making it to go from 1 to n plus 1.
Yeah.
And then,
Right.
the formula for that.
And yeah, so you have something like, if you're making it in a loop,
Yeah.
it'd be like xi equals cosine of I minus 1 times pi over n. Yeah.
Can you explain
Okay. So about the problem not having a solution unless.
Yeah, I remember you kind of talking about it, but I still wasn't following.
Okay. Yeah, there's. Yeah, I did an example on.
I read everything you have,
Yeah.
and everything you said down, but maybe I just wrote the wrong number.
Okay. So the closest thing I have in the notes is on page 24, solving a two-dimensional periodic problem. And there, the problem is solved analytically, but there's a comment there at the bottom about under what circumstances the solution exists. So in other words, a condition that F has to satisfy. And now that's a 2D problem. The similar kind of condition for 1D has to be satisfied.
She also talked about, like, since we don't have an exact solution, you can approximate an estimate of the exact solution by basing it off of matching grid points between, like, different spaces.
Wait, is it about the same thing or?
No, that's a different one.
Okay, all right, okay. Another way to think about it is, all right, so you have F as this Fourier series representation. And so does U. And this kind of similar to what's done in that example, but on one dimension. So, but here you're interested in minus uxx. So from this, you can just go ahead and differentiate this directly to figure out what minus uxx is. And the thing is, both these have e to the ikx in common. So what you have to do is match up coefficients. But what's going to happen is when you match coefficients of minus uxx against coefficients of f, basically you can solve for the coefficients uk hat. So you go ahead and do a differentiation to get that, then match these two. You'll find that in one case you will not be able to get a match unless something is 0. Okay. Yeah.
It's about applying part C, the spectral code.
Yeah.
Is it like the same as question number 4, part B, using Chebyshev points?
Okay. I don't know.
Well, it's periodic, yes.
So here it's spectral for this problem. Is it the same as this one? We can use Chebyshev points.
No, this is 48.
When you have
So, well, you could use FFT, but probably the easier thing to do is,
so no Chebyshev points.
this is the other part of that chapter. Okay, there's a differentiation matrix that has all formulas involving like cotangent or cosecant for second derivative. Use that.
Yeah, I have that. And then from that, go to FFT.
Well, you actually don't need to use an FFT because, in other words, that's how you make your matrix A, and then go ahead and solve a system with that matrix.
So is it okay if I use backslash?
Yeah.
Okay. I don't know why. For some reason, I just wrote a note that instead of backslash, you use FFT.
Oh, well, okay. You could in this case. There be. Okay, the other way to do it is, if you use FFT, and then you. All right, so the matrix for minus second derivative with respect to x goes to. I think I might have written this on the board before.
Yes.
Okay, yeah, you could do that. The thing is, this matrix, is singular. Because it's from the derivative of a constant function being 0. So what you could do is, all right, if I call this A, so A inverse doesn't exist, but pseudo inverse which is written this way is, okay, so F inverse, and same symbol applied to lambda F, where if lambda has these diagonal entries, I'll just call it lambda 1, lambda 2, lambda n, which would come from the eigenvalues of second differentiation, then the pseudo inverse would be, well, you would take the reciprocals. Well, I'll use a plus symbol again, where for a number, lambda I plus is equal to 1 over lambda I if it is non-zero, or 0. So that's how you do a pseudo-inverse. You go ahead and take the reciprocals of the eigenvalues like you would for a regular inverse. If it's 0, you just put in 0. So as long as your F, your right-hand side, satisfies the condition from part A, then it won't be a problem. So what it means is you take FFT of your right-hand side, component-wise divide that vector by your eigenvalues, the ones that are non-zero, and then inverse FFT back, and you get the solution that way. So you're not using backslash. So
But I think the first one is easier, so I'm gonna go with backslash. Is it fine?
I don't care.
Okay.
Yeah.
So another thing is for boundary conditions, do we need to delete those first and last rows? This one?
Not in this problem.
Okay.
Yeah. Because this already takes boundary conditions into account properly, the periodicity.
So I have a question.
Yeah.
Back to 4A. So I made my indexing 1 to n plus 1, and it's taking care
Yeah.
of everything.
Yeah.
And then when I do D, I do the same thing, 1 to n plus 1.
Okay. Okay, for parts A versus B, or
For I think part B for the Chevy.
okay.
Part.
I'm not sure what you're contrasting again.
That's what we had before.
My
Okay.
yeah. So my X matrix, you said in order to take care of that zero, we had to add that extra n plus one, and then when we put it in the cosine, we did j minus one.
Okay.
Do you need to see?
I mean, there's so many different ways to do this.
Yeah.
That's a problem. So I'm saying if you are using a for loop that goes from 1 to n plus 1 to make your vector of x's, in your formula you got to have I minus 1.
Yeah.
Right.
Okay.
I'm now trying to do the D matrix.
Okay. Now that's a different story because it depends on how I and j are being used. So if you have your loop going from I and j, going from 1 to n plus 1, when you refer to xi or xj, you just use xi or xj because those indices are already copacetic with, yeah. However, if you have an I or a j standalone, not an index, but like in a formula, like minus 1 to the I plus j, then you have to adjust, like I minus 1 or j minus 1.
So like in the formula for the off diagonal entries, it's -1 to the I plus j.
Now, there's a funny part there because based on what I said, you could do minus 1 to the I minus 1 plus j minus 1. Yeah, but for convenience, that's the same as minus 1 to the I plus j minus 2,
Yeah.
which is the same as minus 1 to the I plus j and minus 1 to the minus 2.
Okay.
The minus 1 to the minus 2 is 1.
Right. So you can use the same.
So in fact, you don't have to change that one. But if you have an I or j by itself,
Okay.
you gotta change it.
Use that as an index.
Yeah.
Okay.
Yeah.
But that has to go from 1 to n plus 1 for
Yes.
I and j?
yeah, so I'm making an assumption all along. Because you're stuffing this into the ij entry of the matrix, and you have to have positive indices.
Okay.
And it's so much nicer if MATLAB allowed you to index matrices by 0.
Yeah. I didn't,
So to make sure we did, I understood what you said. If we use 1 to n plus 1, we can still use that I plus j, and you said that for the index, and just leave it as I and j. You don't have to.
Yeah, if you're like taking x of I, x of j, don't change those.
Okay. And so I don't.
Yeah, it's only when you have an I or j, like I think they only come up as part of an exponent.
yes. That's
Yeah.
the only time.
Yeah.
Where?
That one right there. -1 to the
Yeah,
I plus.
but you still don't have to change this one, but other ones that have only I or only j,
But I don't think we have.
For future.
on the boundaries, you do.
Where?
You keep ignoring the boundary entries.
I keep forgetting. Okay. See, I'm looking at the notes that I took from the other day, and I don't see anything.
Okay, maybe I didn't write those down then, but
Scroll down, you gave us this.
okay, that's not everything. Go look at the notes. Yeah, because back then I messed up,
Oh.
and I told you about that later.
Okay. Yeah.
Okay,
Okay, I'm looking at the notes.
and you see all around the edges,
Uh-huh. Yeah.
Yeah.
So we need to put those in there.
you need those entries.
So we need to put those in there when we're making D.
Yes.
And then we square D.
Yeah.
And then we cut off the
Yeah.
outside.
Yeah, and then for your first derivative matrix, you just cut out those rows and columns after you put them in there.
Okay.
So we have to add that top row, bottom row. and the
Yeah.
side.
Yes. And yeah, and some a lot of those entries have like only I or only j in an exponent. There you have to shift. There you do need to shift it.
Minus 1. Sorry.
This is why I'm so scared to make a mistake in class because then it just sticks. Yeah.
So once we add the boundary, that's when we square J.
Yes.
Square D.
Yep.
And put it in that formula to get you.
Yep. Okay. Any other? Okay. So now, Continuing on with time-dependent problems. We're really focusing on whatever system of ODEs you get after you discretize your PDE in space. So we're dealing with y prime is equal to f t y before. And last time I covered explicit Euler and implicit Euler that are only first order accurate. So how to get higher order accuracy? Because the thing is, when you discretize in space, usually you're getting at least second order accuracy, if not more, like or h squared or whatever. But then if you're only getting first order accuracy in time, then why go to all so much trouble to get higher order accuracy in space? Then you still have this large error in time. So we want to try to get higher order accuracy in time also. And there's various ways of doing that. One is to add terms to whichever Euler's method to match higher order terms in the Taylor expansion. Of y. So to give you an idea, even just going out one term, we have y of tn plus 1 is the exact solution. So I just Taylor expand it. So you get y of tn plus delta t y prime, but y prime is equal to f. So going out this far, this is explicit Euler right here. But we already know it's only first order accurate, so then we want to add on the next term of the Taylor series. That would be delta t squared over 2 times y double prime of tn. But the thing is, now I need to express y double prime in terms of f. Oh, so that's the same as derivative with respect to t of f of t y of t evaluated at time tn. So now what I need to do is take partial derivatives of f with respect to both of its arguments, because both of those depend on t. So this would be equal to partial of f with respect to t at tn y of tn plus partial of f with respect to y at tn y of tn. By chain rule, you have to differentiate what's in here with respect to t also, y prime, but that is f again. So if I stopped here, so in other words, I just added this term, so delta t squared over 2 times all this, then I would get second order accuracy. But we don't really want to do this, because what if it's not really convenient to get partial derivatives of f with respect to its variables? Now, if f is a relatively simple function, and you have this on hand, then great. But if we don't really want to assume that if we don't have to, and we don't have to. There are other ways to get high order accuracy without going to this trouble. Because these expressions for high order derivatives of y in terms of derivatives of f, they just mushroom in complexity. So then the next one will be a lot worse. So, but the idea behind this can still be used to get higher order accuracy in a more practical way. And that leads us to a very well-known Runge-Kutta methods. So the idea behind Runge-Kutta methods is to evaluate f at several points, and then to figure out which points you can do Taylor expansion of f and match that against the Taylor expansion of y over there. And when I cover Runge-Kutta methods like in upper classes like 772 or 561, I actually do that for a simple example, and it's not simple. But I'll give you the general form of Runge-Kutta method. So it starts out looking like Euler's method, but instead of a single evaluation of f, we have a sum involving these quantities, these k vectors, which I'll define now. So each k vector is an evaluation of f at some chosen t. So it's always Tn plus some multiple of delta t. And then the second, all right, where the recording cut out again, I've gotten this far. So evaluate f at certain times, so Tn plus some multiples of delta t, and then some y argument, it's always yn, plus some linear combination of these same k vectors. And so R refers to the number of times we evaluate f. So we call this a R stage Runge-Kutta method. The dominant expense in a Runge-Kutta method is the evaluation of f. F might be a very simple function, but it may not be. So we want to try to evaluate f as few times as possible, but still get as high order of accuracy as we can. So there are many different Runge-Kutta methods out there that all can be written in this form. Okay. Now, so some examples of Runge-Kutta methods. Well, actually, explicit Euler is a Runge-Kutta method. The explicit midpoint method. So that would be K1 is just plain old f of Tn, Yn. Usually that's what K1 is, because I was always going to use this for something. And K2 is f of Tn plus delta t over 2. And then we want to have an approximation of y at time, at this time. So taking half a time step. So that would be yn plus delta t over 2 k1. So this is actually the explicit Euler approximation of y at Tn plus delta t over 2. So that's a reasonable approximation to plug into f to get the value of the time derivative at time Tn plus delta t over 2. And then we just let yn plus 1 equal to yn plus delta t k2. Now, to give you an idea as to how this method contrasts with explicit Euler, we can actually look at the integral form of the ODE. Because if we have y prime is equal to f of ty, then y of t. I'll fill in the of t here too. Okay. If I integrate this equation, both sides, from Tn to Tn plus 1, I get the exact solution satisfies y Tn plus 1 equals y of Tn plus the integral from Tn to Tn plus 1 of f of s y of s ds. So you can think of many different time-stepping methods as attempts to approximate this integral using some quadrature rule. So explicit Euler approximates an integral of f of t dt very simply, just by taking the width of the interval times f evaluated at the left endpoint, Tn. So it's a pretty crude approximation. Implicit Euler use the approximation b minus a f of b, but value of y at time b, or Tn plus 1, is what you're trying to compute, so that's why you have to solve an equation to get it. Explicit midpoint uses a midpoint rule, approximates it by b minus a f of a plus b over 2. So it's trying to approximate f at the midpoint of the interval of time, which it uses here, but then it needs an approximation of y at the midpoint of that interval of time. That's not readily available. That's the solution we're trying to compute. So it uses an explicit Euler approximation of that. And that is enough to get second order accuracy. But it had to, now on one hand, each time step takes twice as much work as explicit Euler, because it has to evaluate f twice instead of once. But because of having a whole higher order of accuracy, like you're doing twice as much work per time step, but your error is squared from before, so a lot smaller. So it's worth it. So, okay. All right. So for example, when you cut the time step by a factor of 10, your error is reduced by a factor of 100. So it's definitely worthwhile to be doing twice as much work per time step. Okay, so that's one of the simpler Runge-Kutta methods. There's also, wait a minute, what's the difference here? Oh, okay. You can also express implicit methods. Okay. You can also describe implicit methods as Runge-Kutta methods. For example, the implicit midpoint has K1 similar to K2 in explicit midpoint, same time value, and then similar, and it looks like it's the same y value also. And then you just have yn plus 1 is equal to yn plus delta t K1. So, but the thing is, what makes this harder to implement than the previous method? It's a very subtle difference. So how come this is not as simple as simply plugging things into F and then seeing what you get?
There we have K2, but here we have K1.
Yeah, K1 on both sides.
Right.
So you actually have, this is actually a nonlinear equation you have to solve for K1, which could actually take a whole lot more work. So you might think, oh, this is half the work of the other. Not really. There's likely to be more work per time step. But as an implicit method, you can get away with fewer time steps, so it can still be worthwhile. So the implicit method, you have to solve an equation, and that's what ends up happening here. Now, another, this is also second order. Okay, another is the explicit trapezoidal method, which is based on the trapezoidal rule for integrals. So you have the same K1 as in the implicit midpoint method, and then you have K2 is intended to approximate F at time Tn plus 1. So we have Yn plus delta T K1. So this is the explicit Euler approximation of Yn plus 1. And that gets fed in here to approximate F of Tn plus 1, Yn plus 1. And then we get Yn plus 1 this way. So it's delta T over 2 K1 plus K2. So the idea here is this is using approximation integral of F is equal to T minus A over 2 F of A plus F of B. So that's the basic trapezoidal rule. And this is also second order. There is also an implicit trapezoidal that just puts Yn plus 1 there. That's what makes the method implicit. Actually, I think it's not in the notes, but, well, it kind of is, but in a different form. I want to try to describe implicit Euler as a Runge-Kutta method. I could say that K1 is equal to F at Tn plus delta T, and then Yn plus delta T K1, and then Yn plus 1 is equal to Yn plus delta T K1. And these expressions are exactly the same. So this is Yn plus 1. So put together, you have this nonlinear equation to solve for Yn plus 1. So that's this is how you can describe implicit Euler as a Runge-Kutta method. Now, let's see. That's what did those. Okay. Now, the best known Runge-Kutta method is, let's see, actually, I want to leave that up there. Yeah. The fourth order Runge-Kutta method. Doesn't like probably. Yeah, it's certainly one of the most often used because it's pretty simple to code up. Gets fourth order accuracy. Okay. All right, so here we have 4 evaluations of K. So K1 is the usual, evaluating at Tn. K2 and K3 evaluate at the midpoint in time. So this is an explicit Euler approximation of y at the midpoint in time. K3 also at the midpoint in time. Whoops, that's delta t over 2, not 3. Not sure what I was thinking here. Yn plus delta t over 2 K2. And then finally, Tn plus delta t, Yn plus delta t K3. So each K feeds into the next one. And then we have Yn plus 1 is Yn plus delta t over 6. And we have K1 plus 2K2 plus 2K3 plus K4. This is kind of like Simpson's rule for integrals. So for the integral of f is approximated by b minus a over 6 f of a plus 4 f of b, or midpoint, a plus b over 2, plus f of b. Similar thing down here, because both of these approximate f at time Tn plus delta t over 2, but midpoint in time. So the midpoint is given 4 times as much weight as either of the endpoints. So it's loose resemblance, but it's there. And this is, well, as the name says, 4th order accurate in time.
Excuse me, I just forgot that Simpson wasn't 4th order accurate.
It is, yeah,
Is it?
yeah. Okay. All right. So I think it's in the notes. I won't go into it here, but in the notes, there's a form for expressing Runge-Kutta methods called the Butcher Tableau that is where all these coefficients that define Runge-Kutta method, the C's, the B's, the A's, are all put together. So all Runge-Kutta methods can be described in that manner. And what's interesting is in the coefficients, the A's, end up forming a lower triangular matrix. Well, actually, if you take the whole tableau together, it's a lower triangular matrix, unless it's implicit. If it's implicit, then it kind of breaks that structure. Actually, when a couple implicit methods we have here, it's more like upper triangular. Okay, so but it's more like it's a more compact way to describe these things, and that's I've seen it used in actually, like for instance, some of Maya Tokman's papers. Okay, so we'll take a break now, and then I'll talk about other time-stepping methods when we come back. Okay, so I guess there won't be much video for the rest of this because we're talking about homework. Let's see. So problem 5C, Fourier spectral. The FFT approach. They use. Okay. So since there seems to be some trouble working with the regular differentiation matrix for a spectral, we'll see if there's something wrong with that, but I'll have to look up in Trefethen's text. So the other way of solving this problem, FFT approach. So you have your vector F, that's your right-hand side. Pass it into FFT, you get a vector out, it's a Fourier transform. So this gives you like the coefficients Fk hat. Then I'll explain this in a second. We're multiplying by a diagonal matrix. So you still have a vector, and you pass into IFFT, vector comes out, and that's your solution U that should naturally have zero mean. Now, Fk hat, or so if you do, for instance, G is equal to FFT of F in MATLAB, then the vector that comes out will contain the frequencies in this order. The order is very important. F hat 0, which ought to be 0. F hat 1, F hat 2, up to F hat n over 2, we're assuming n is even. And then we do F hat minus n over 2 plus 1 all the way to F hat minus 1. So the frequency, Fourier series coefficients are naturally ordered that way by FFT. So I'm explaining this is what it gives you. Therefore, you have to take into account which frequency goes with which element to handle the multiplication by lambda plus. So, so each G, okay, so F hat K goes to, so as far as multiplication by the pseudo-inverse of the matrix of eigenvalues, so it would go to Fk hat over k squared if k is non-zero, because when you differentiate twice, you get ik squared, which is minus k squared. But this PDE is minus uxx, so it's just going to be k squared. And then you're undoing differentiation, so that's why you're dividing by k squared instead of multiplying. And then it's going to be 0 if k equals 0. So basically what you can do is you're going to multiply all of these by whatever you get here, and then, so F goes for FFT, then whatever you get out of that, you multiply by, or you divide by k squared if k is non-zero, and then the result of that gets fed into IFFT, and out comes your U. So MATLAB is doing most of the work for you. You just have to handle the division.
Input is F, output is U.
Yes. Yeah, so basically it's going to be, it's a three-stage process. FFT, divide, IFFT, that's it.
And you said that this way FFT naturally has the mean, so you don't need to use that for you.
Well, this ensures your solution will have zero mean. Yeah, and that's something that actually surprised me from part B, the finite difference code, that it produced a solution that had non-zero mean. I wasn't expecting that.
But I'm guessing that you mentioned once why you're using zero mean, but could you please just tell me again?
Well, the way it's supposed to work is once a solution exists, if f has zero mean, you have infinitely many solutions. So you could add any constant to a solution and still have a solution, because you plug it into a PDE, you differentiate it, it goes to zero anyway. So you could say, well, so really the simplest solution in a way is to have zero mean. Also, it has a minimum norm for your coefficients. I just thought that backslash would produce the minimum norm least square solution, which would have zero mean, but it didn't. So I'm not sure what criteria it's using instead. But yeah, it's just sort of a preference thing, I guess.
What is K here?
Well, K is the frequency. The subscripts here, see?
Okay.
Now, it's not the index into the vector. So when I'm saying
I
that,
can define something else. I cannot use my and kind of try to.
well, here's what you could do, like you've actually done in your own research code. You could define a vector that has these values in it. That way, so you can do something like GK is equal to, well, actually, you don't want to do that. It's something like that, if K of J is non-zero. So that way, you can use your natural indices, 1 to n, to pick out the correct K value. And then once you do that, that gets fed into IFFT.
We're using the same number of points, and our code looks the same, but when she runs hers, she doesn't have any oscillations, but I do. But we use the same amount of points. Hers just goes up like this and it comes down.
Okay.
That's my list.
You don't have any oscillations anymore?
It is, but it's very, very small.
Right. But
Your
hers doesn't
scale,
have-
what
hers
about your,
doesn't have any at all.
what about your axis?
Mine,
Okay. Really close look at both of these.
it might be, because hers starts at 0, mine starts at negative 0.5. But I don't think
Wow.
I'm just checking.
Yeah, what will be different.
What's your epsilon?
my epsilon is 10 to the negative 1.
Unless there's some slight difference, I would introduce some round-off error or something, because I mean, this is a very ill-conditioned matrix.
I'm gonna give you.
I don't think so.
Okay. Yeah, I don't know then.
Okay.
Okay. Well,
Yeah, we use 200 in this one. That's weird.
okay. Barbara, any other homework questions?
You probably answered 5. I was working on 4 when you were talking about 5. So I don't want to ask you redundant questions, so maybe I just want to go first.
Okay. All right. I really want to use the last part to cover stuff.
Okay.
I'm behind. So. All right, so Runge-Kutta methods are called one-step methods, even though they might be several evaluations of F, but they're called one-step methods because we only use info on one time interval, tn plus 1, to go from a solution at time tn to time tn plus 1. So by contrast, multi-step methods they go further back in time. And the reason for that is they perform just as many evaluations of F as Runge-Kutta methods, but they reuse evaluations of F. So there's only one new evaluation per time step. So multi-step methods can be much more efficient on a per time step basis than Runge-Kutta methods. So the general form of an S-step multi-step method is, on the left side, you have a linear combination of y values at various times. And on the right side, you have a sum of, not 0 to infinity, 0 to s. That would be weird, infinite step method. Some linear combination of f values. And I can use the abbreviation fj, well, actually, f n plus j. So in general, fn is a shorthand for f at tn yn, just to be more concise here. So multi-step methods, they don't have all these weird expressions that are substituted to f like Runge-Kutta methods do. They just do tn, yn, tn plus 1, yn plus 1, and so on. Now, the method is explicit if beta 0, no, beta s is equal to 0. Otherwise, it's implicit. Because the idea is the largest index, which would be n plus s, that's the y value you're trying to solve for in terms of previous y values. So if you have f n plus s in here, that is f evaluated at the y value you're trying to compute. So that causes a nonlinear equation. So just the coefficients alone can tell you if the method is explicit or implicit. Now, there are a few well-known classes of multi-step methods. I think I'll get through these and call it good, because I only have a few minutes left anyway. Okay. Now, this is not meant to be exhaustive. There are multi-step methods that do not fall into any of these categories. There's Adams Batchforth. These are explicit. And they can be identified by, okay, so for all of our So we only have these two alphas. So you always have a method like this. Yn plus 1 is equal to Yn plus they always have this form. Where j goes from 1 to s. So remember, 0 to s minus 1. So beta n plus s must be equal to 0 for it to be explicit. Explicit Euler is an example, not only is it a Runge-Kutta method, it's also a Adams-Bashforth method, but just a one-step version. And the accuracy is order delta t to the s. So you could choose, that is s minus 1 there. Okay, to leave out that final beta to make it explicit. We also have the rest of the Adams methods, Adams-Moulton. That has these same alphas, but beta n plus s is non-zero to make it implicit. So except for some going from 0 to s, it has the exact same form. And order delta t to the s plus 1 accuracy because of the extra evaluation of f. And finally, we have backward differentiation formulas, BDFs. Adams methods come from approximating the integral of f, like from the integral form of ODE. BDFs is higher derivative approximations of y prime. So beta n plus s is non-zero. All other betas are equal to 0. So, okay. And then the order of accuracy is like Adams-Moulton, order delta t to the s plus 1. And the very last thing I will do is give a few examples of these methods. We have, for instance, Yn plus 2 is equal to Yn plus 1 plus delta t 3/2 Fn plus 1 minus 1/2 Fn. So this is Adams-Bashforth. It only has these two y's, which makes it an Adams method. There's no Fn plus 2, that's why it's an explicit Adams method, therefore Adams-Bashforth. So this is two-step, so second order accurate. And then we also have, Yn plus 2. This is a two-step Adams-Moulton method. So that's a 5. And because it's two-step, it's order delta t cubed accuracy. So it's doing a little more work than this two-step Adams-Bashforth method, but we get extra degree of accuracy as a result. And finally, so this is Adams-Moulton. And finally, an example of a BDF. This is a two-step method. So implicit Euler is a BDF, actually, but this is a more interesting example. so this is two-step. So all of these are two-step methods. So the explicit one and the second order accurate, the other two, the implicit ones are third order accurate. This is a stencil for first derivative using a second order backward difference. So we're evaluating a derivative at x naught minus h, and x naught minus 2h. It's kind of like a problem homework 1 where you had a non-symmetric stencil for a second derivative. This is for a first derivative. So this is, I actually teach this numerical differentiation scheme often like 772 or 560. So this is y prime is equal to f at time. And actually, I totally goofed. Derivative at x naught is using value at x naught minus h, x naught minus 2h. So it starts at this point and moves that way. Okay, that's it. I just want to get through that section, so then I could deal with everything else tomorrow, which is the last day we have for this. Okay. That's covered the multi-step methods ever.